Welcome guys. So this is my second videos about introduction of the group and the algebra. And so today I will talk about how to construct the representation of the algebra sl2c. And yeah, I hope you guys subscribe to my channel. So let's quickly start. Let me just add more pages so that I can use all of it. Okay, so hope you guys subscribe to my channel. Okay, so today let's just so this is introduction video, right? So let's talking about a representation of sl2c, and hope to start from here to see some representation of sl3c, and hope to see some ideal code root system. So I will explicitly construct these in details, but for the rest of it, I will just talk about some hint, and then in the future I will make a whole video list about the algebra and the groups. Yeah. Okay, so sl2c is the ABCD 2x2 matrices, and all ABCD are complex number, and such that A plus D is 0. So basically, trace this. Yeah, traceless. So it's traceless, right? So you can view this as like sl2c is a three-dimensional vector space. So it's like a C cube, and you can write ABCD, right, as A00 minus 1, B0100, C0010. So standard notation, this is H, and this is X, this is Y, right? So these are bases, okay? So your Lie algebra is basically span of H, X, and Y. So it's a three-dimensional vector space, and your easy exercise is to compute the commutator. Okay, so I will not compute for you. This is a very simple exercise. Okay, yeah. So our goal is to construct finite dimensional representation of G. Okay, and yeah. Okay, so let's see the idea. Okay, so this is the in the quantum mechanics, there's a creation and annihilation operator, but similar as it's exactly the same as this group, the algebra representation. But the relation is very complicated, so I will not talk in that part, but I will give the construction for this one. So your H, let's consider your representation, right? X on this be alpha, right? So let's say and I define the right. So I right, if V belongs to V alpha, that means that H on V will be alpha V, okay, or basically HV. Okay, so now what I'm saying is that suppose this V is your representation. So now H becomes some abstract or the V n by n matrices. N is a dimension of V. Okay, so let's assume that this is our representation, and alpha is the eigen value of H. Okay, so yeah, so HV is alpha V, and then one can easily check that. How about HXV, right? By the commutation relation, this is HXV plus XHV. So this is 2 plus alpha V. And then you can easily prove that if you check on Y, it becomes alpha minus 2V. Okay, so which tell you that your X will map V alpha into V alpha minus 2. Okay, so now this gives you a hint of the lattice, right? Because you minus 2, minus 2, minus 2. If you can keep minus 2, then you will go to the negative infinity, then this original vector space dimension will blows up. So this gives you the constraint about finite dimension. Okay, so V is also from Y V alpha from V alpha plus 2, and the H will fix V alpha. Okay, so the standard diagram looks like this. Oh, sorry. So in order to, as I said, right? So in order to make V finite dimensional, the constraint is that the difference, right? The difference must be differ by 2k, right? So basically, the picture must looks like suppose you have Vn, right? Then your H will fix in the Vn, and when you add on X, then it becomes Vn minus 2. When you add on Y, so this is Y, and then this is your X, this is your Y. This is Vn minus 4, and this is X, this is Y, and Vn minus 6, and the H will become will fix into this. H is a self loop, and there is something goes here, right? X and Y, and you so this is Vn plus 2, and you keep going, right? So in order to make this diagram finite, right? I mean, you can easily check. In order to make this guy finite, okay. Let's see, right? So for example, if n is 0, then you only have V0, right? If n is 1, then you should get V1 and V minus 1. N is 2, V minus 2, V0, and V2. Right, so I think up to now, so from this picture that you already get the answer. Although I did not rigorous to prove it, but you can easily say that given any integer positive greater or equal to 0 integer, there exactly has one representation of sl2c. And so as a SU2 case, that I will prove that this guy is irreducible. Okay. Okay, so now let's go to a rigorous proof. Yeah, so I mean the previous picture I just give you some intuition, right? So let's give it a previous proof that this guy is irreducible. Okay, so let's V belongs to Vn. Then let's say V is by Y V, and then Vy squared V Okay, and keep going. Okay. Okay, and let's say suppose V is irreducible. Okay, so I should say I want to claim that V is irreducible, and I see what is the constraint. Okay, then yeah, so so you need, in order to right, so we need to check that so since V is irreducible, right? So we need to check that this YKV is stabilized by sl2c. Okay, so basically this means that this set is stabilized by acting on the Y, X, and H, right? This is the definition of irreducible, right? Irreducible means that this is the invariant subspace. So yeah, if you really group the algebra element act on this subspace and it did not go out of them, that means it forms a representation. Okay, so obviously that if you act on Y, then yeah, so Y is a trivial, right? So if act on Y is still YK. So remember that up to now I didn't make a cutoff on this side. I just suppose that there is a V and you can keep going. Okay, so Y is trivial, and you act on H is a trivial, right? Because when H act on Y, it becomes Y of something. Y plus become another you just change the eigenvalue. Okay, so the only non-trivial part is X. Okay, so how about let's say let's compute XLV, then it become x, y, v, v plus y, x, v. Okay, so let's make an assumption. So our assumption is that you start from v and keep any heating, right? So that's supposed. So in order to make it finite, right, you must put some vector here v such that x v is 0, right? So let's say this is v, and you keep using y to go back. Okay, so our condition is that x v is 0. So basically, go back to this proof, right? Now I want to make this finite dimensional, so I must assume that there is a guy v which is cannot be keep going up, right? So this guy will be annihilated by x. Okay, so yeah, this is hv. So let's say nv. So up to now I didn't say n is a integer. I just say that n is some number. Okay, and xy squared v. Basically, it's the same thing. You can easily prove that this is xy yv plus yx yv, right? And this guy is hyv plus ynv. So it's n minus 2yv, right, plus nyv, so which is n plus n minus 2yv. Okay, and you can easily check by yourself. This xyv will be n plus n minus 2 up to n minus 2m plus 2 ym minus 1v. So it become ym minus 1v, and then this is n. So it become m times n minus m plus 1 ym minus 1v. Okay, so things need to be finite dimensional, right? So now I can put a cutoff on y, right? So let m be the smallest, right? So that means there should be a things is finite, right? So m be the smallest, let m be the smallest integer, such that ymv is 0, right? Okay, so but if m is the smallest integer such that the ymv is 0, that means what? That means the m or n minus 1, n minus m plus 1 should be 0, right? But m cannot be 0, right? So the only case is n to be m minus 1. Okay, so what I'm saying is that m is n plus 1. Okay. So what do we mean by m is n plus 1? That means our vector space generated by v and yv, y squared v, up to what? Up to ymv, right? But it's 0. Okay, so this is our nth dimension of v. It's just n plus 1. And for each alpha, right? So this now I can write the alpha. So this alpha start from minus n plus 2 up to n minus 2n, right? Because now okay, so now it's very important. Now n can be an integer, right? N can be positive integer, right? Because m is a positive integer, right? So now n can be positive integer, right? So now this is our v. So our final representation will be v direct sum of alpha v alpha, where alpha belongs to all of these, can be all of this, and each dimension of v alpha is 1. Okay, so this is what we just proved. Okay, so this is the standard results, right? So basically the final results will be just what we're gonna to prove is that each irreducible, I should say finite, each finite irreducible representation of sl2c is isomorphic to, let's say, because we just solving every irreducible representation by this method, right? Is there was some by this v alpha, where alpha belongs to minus n plus 2 up to n. Okay, and then your n is some greater or equal to 0. So and the dimension of v alpha is just n plus 1. Sorry, dimension of v is n plus 1. So that means dimension of each alpha is 1. Okay, so this is exactly the same as the spin, right? If you work in the physics, then this is called spin. Yeah. Okay. So some guy will denote this by V upper script n. Okay. So to make superscript n, so to make this whole vector. Yeah. Okay. So this is a finite. This is all the finite dimensional representation of sl2c. And the proof is just using the similar as quantum mechanics, but basically you write down every the algebra and assume that your V is finite dimensional. So you will make some vector which initiated by x, and you go y and go another directions, and you need to prove that things is finite, right? So you will get something. Get all the structure. Okay, so yeah, this is just my yeah, and there's a thing called a character, and then there's a thing called a CG coefficient. I will not talk in this video. And in the future, that maybe in the next video, I will give you a character and the CG coefficient, and I will prove something. The spin addition method basically is basically if somebody give you the two representation vi vj, right, then you should be decomposed into some k, right, with some k. So this is like a fusion algebra. Right, so as a finite group case, that tensor can two irreducible representation tensor can give you a split of another representation. Okay, so especially in this case, that the CG coefficient in general should be very difficult, and then there's a thing called wild character formula. Which will give you the better, give you the powerful tool to get for you to get a decomposition. Okay, so yeah, this is not a this is not general. This is not just a simple story for sl2c, right? So let me just quickly mention that what will be if you're talking on sl3c. So if you're looking on sl3c, and there's A generators, and then you can decompose this G into, let's say, eta direct sum of this. This is G alpha alpha. Okay. Yes, should be here. Okay, now this is called the maximum Cartan subalgebra. Okay, so in this case, the maximum Cartan subalgebra is 2. Right, so basically that means you can make. Okay, so let me just write something, tell you something which is very sketchy. Okay, so in the sl2c, in the original sl2 case, right, you can view your world has some center which is h, and the x and y are both the eigenvector of the h. Right, so basically eigenvector means that hx will be something x, and then hy will be something y. And this is not a coincidence, right? So if you're working on a Cartan subalgebra, which is dimension 2, that means that now you can find h1 and h2, right? Such that your h1, and there's a 6 element, let's say e1, e2, e3, e4, e5, e6, and then your each hi econ is ej, where I from 1 to 2 will give you a vector, right? So basically it will give you, let's say I should use j, right? You get some j1 to jihi. Okay, so very bad notation. But what I just want to say is that let's say, so if h1 econ e1 and the h2 econ e1 will be something e1. Basically, you can find such basis. So that means you can plot e1. You can plot e1. You can plot your e1 as a 2-dimensional lattice, right? So basically, you can plot your e1 as 2-dimensional lattice, and your e2 to be another 2-dimensional lattice, and e3, and the e4, and the e5, and the e6. Okay, so this is the general story, right? So that means given any Lie group, then you can decompose. You can first get the so-called maximum Cartan subalgebra, and every guy become the Cartan subalgebra, right? And these this guy is called roots. Okay, so that means each generators. So this is just very sketches. So each generator will become a vector, the finite dimensional vector, and the dimension, right? In the n dimension. So this n is the number of the number of generator of this Cartan subalgebra. So usually people call it rank G. Okay. So now each guy become a lattice vector, become vector. Okay. And then you can separate this vector into two, separate into the two parts. Okay. So the first part, right? So there are 6. So you can separate into 3 parts, 3 and 3, and the sum of them, right? So the half of it is called the positive roots. Okay, so I will not explain it, but I will explain in the future. And the rest are called the negative roots. So basically, there's a okay. And then the key formula is that let's say you can prove that if you label, now you can label each irreducible representation, each Lie algebra generator as a vector alpha, and if I count beta, then you become G alpha plus beta. Okay, so this is very now each generator can be labeled by some vector alpha. And the adjoint representation become the addition of the vector, right? So in order to make this finite dimensional, there will be hard constraint. Okay, so you can suppose now your representation is V, is direct sum of this GBV alpha, where B becomes so-called negative roots. So R is a set of roots. Okay, so the idea is that you need to assume that all this vector is annihilated by the positive roots. Okay, then generated by negative roots. So this is why in the sl2c case that you have the x and y and the h, right? So you need to assume your vector v is annihilated by something x, and the x and y go back. The only difference is that in sl2c you have 2 guys which you need to kill, right? So basically the idea is that you need to find some v which is killed by the 3 positive roots. Okay. Right. So basically, you should have some v which you kill by 3 positive roots. Let's say this is E12 and the E13 and the E23. Right. So basically, you need to assume that there is a vector v, and all the representation is comes from the rest, right? So the rest of and your vector space will be, let's say, E. So basically, it's all the 3 negative roots, and all its products on V. Okay, so this is your irreducible representation. Okay, so basically you can plot it as a hexagon. Okay, so this is the general story. This is the general story. Okay. So this is called the highest weight representation. Okay. And this is the famous theorem results in this V is called the highest weight vector, and the famous theorem in the algebra representation is that actually all the compact Lie algebra the representation comes from the highest weight representation. So highest weight representation, that means that you choose a vector which is annihilated by all the positive roots. Okay, and this guy will, and the theorem just tell you that this guy must be irreducible. Okay, and the proof is similar to sl2c. Okay, so let me just finish this thing. Okay, so one can construct a so-called root system. I will give the root system introduction all the classification in the future, but let me just quickly mention. So R is called root system is if let's say R. So R is a subset of the Euclidean space. If first one is that R is finite, and span Rn. Okay, so n is something which is greater or equal to 2, greater or equal to 1. Okay. And the second is that if alpha belongs to R, then net minus alpha belongs to R. And the third is that if alpha belongs to R, then you can define a so-called wire transformation. You pick alpha, W alpha. Yeah, we'll map R to R, right? So basically, you can construct something linear transformation and then force to make R to R. So basically, each vector account by this W alpha must be in the root system. And the first one is that for any alpha beta belongs to the root system, you can define n beta alpha to be the inner product of beta alpha and alpha alpha. Then this guy must be a integer. Okay, and then you can check that if you define this and you define n alpha beta and you times it, then you will get something. Yeah, and you will prove that the only possible angle is basically if theta belongs to pi over 2. Then so n if n becomes pi over 2, that means the two roots are perpendicular to each other, right? So that means so people use this dot. So this dot, each dot is a generator. Okay, so this is alpha, this is beta, and then also theta can be 2 pi over 3. I guess it's 120 degree. So use one line, and you can say that their lengths are the same. Okay. And also theta can be 3 pi over 4, which is 135 degree. So use 2 lines. And one of its the length is greater than another is square root of 2. And then theta is 5 pi over 6. So this is 150 degree, and it should have 3 lines. Okay, and if you assume that this root system is so-called irreducible, then you will get the following so-called thinking diagram. And if my understanding is correct, this classifies all simple, complex, compact, finite dimensional the algebra. Okay. So this is a very beautiful result. So basically, thinking diagram contains an class, which is just this. So that means you have this is just plot is a number of the. It's not a number of generators. It's a number of Cartan subalgebra, right? So I only plot Cartan subalgebra. Okay, and this suppose you have n of them. I think this is corresponding to the SL n plus 1c. So if n is 1, right, then you should have only one dot. Become SL2, right? So if I plot this dot, just 1, then it becomes SL2c. Okay, and but you know SL2c has 3 generators, right? So this is the only root system. So this root system looks at just 3 dots and a 1 dimension. Okay, and then there's a Bn, which is this. Okay, so you can use the classical mathematics to prove that if you these are all the possible root system, and the proof is not so difficult, right? And the final become should be something, and this corresponding to SO2n plus 1c. And also there is a thing called Cn, which is the same as Bn. The only difference is that the final 2 lines are different, right? So this is the S-symplectic group, which seldom people understand what the hell is going on. Okay, and Dn, which is this, n greater or equal to 4. This is called SL2nc. Oh, by the way, so this guy need to n greater or equal to 2. This n greater or equal to 3. Okay, and the final is the 5 exceptional case, which is so famous, so called the exceptional Lie algebra. Okay, so the first one is a G2, which is okay, mathematically you can prove that I mean the root system cannot I mean this is the only possibilities. You can prove that if you add this one, then you will violate something very fundamental. Okay, and I will give the proof of this root system in the future. Okay, and also called F2. Oh, sorry, F4. And why F4, right? Because there are four points, right? 4 dots, two. Okay, and also the famous E6. Okay, and E7. I think you add this, and also E8. So E8 is a soft. E8 has 248 generators, and corresponding to something in a string theory, which nobody understands what's going on. So, okay, so this is the thinking diagrams. And yeah, and you can prove that I mean, in the future, then I will give the formal proof that why you cannot. So it's very important that you this dot must add in here. It's not, you cannot shift it. Okay. And but because they will violate the axiom of the root system. Okay, so this is the very quick general introduction of the algebra. I think only 2 videos. Yeah, previous one and this one. And then in the future, that I will start to do it step by step. So these 3 videos just for you guys to, or I mean, for you guys and for me to just have a little fun. See you guys next videos.